the largest steam locomotive ever built, sat cold and silent for over 50 years, rusting in the California sun while millions of visitors walked past it. This is the story of why the mighty Big Boy 4014 was left behind, and how it finally roared back to life. In November 1941, workers at the American Locomotive Company plant in Schenectady, New York, completed builder number 69,585. This machine, delivered to Union Pacific that December, was designated number 4014. It belonged to an elite group of 25 colossal machines known simply as the Big Boys. Number 4014 was the 19th unit built in this class, designed to push the boundaries of steam-powered transportation. To understand the sheer magnitude of number 4014, one must look at the raw physical dimensions. The locomotive and its tender stretch exactly 133 feet in length, a distance that outmeasures a standard Boeing 737 passenger jet. Fully loaded with fuel and 30,000 gallons of water, its service weight surpasses 1.2 million pounds. This immense mass is distributed across a specialized 4884-wheel configuration, which features a 4-wheel leading truck, 2 separate sets of 8 68-inch driving wheels, and a 4-wheel trailing truck. This articulated design allowed the massive frame to pivot, enabling a locomotive of this length to navigate curves on the main line that would otherwise derail a rigid engine. Every component of number 4014 was engineered for maximum power and structural endurance. Its boiler operates at a high pressure of 300 pounds per square inch, directing steam into 4 simple expansion cylinders through Walschaerts valve gear. This system produces over 6,000 horsepower, generating a tractive effort of 138,240 pounds. American Locomotive Company built number 4014, not for speed but for raw pulling power. It was designed to run continuously day and night, handling the heaviest freight trains of the era. The machine represented the absolute pinnacle of American steam engineering, built at a time when the nation's railroads faced their greatest operational demands. The rugged terrain of the American West dictated the terms of railroad operations. For Union Pacific, the ultimate bottleneck lay in southwestern Wyoming and northeastern Utah, along the Ogden to Green River route. Here, the tracks cut directly through the Wasatch Mountains, forcing heavy transcontinental freight trains to battle a sustained 1.14% grade. By the late 1930s and early 1940s, the volume of freight surged, moving millions of tons of steel, coal, and military equipment across this mountain pass became an operational challenge. Standard locomotives lacked the tractive effort to conquer the grade alone. To get a single heavy freight train over the summit, Union Pacific had to resort to coupling multiple locomotives together or utilizing helper engines stationed at the base of the mountains. This practice was highly inefficient, requiring extra crews, consuming massive amounts of coal and water, and causing severe traffic congestion. The railroad needed a machine capable of pulling a 3,600-ton train up the Wasatch grade completely unaided. But building a locomotive with that level of pulling power presented a severe engineering paradox. A traditional steam locomotive relies on a rigid frame to align its driving wheels. To get more power, engineers had to add more driving wheels, which meant lengthening the rigid frame. However, a locomotive with an excessively long, rigid wheelbase would derail on the sharp 13-degree curves winding through the mountain canyons. The critical mechanical answer was articulation. Rather than utilizing a single rigid frame, designers split the driving wheels into 2 independent engine units. The rear set of drivers remained rigidly aligned with the boiler, while the front set was mounted on a hinged frame that could pivot laterally. This allowed the locomotive to literally bend in the middle. When entering a curve, the front engine swung outward, guiding the massive boiler smoothly along the track geometry. This specialized arrangement, coupled with the Walschaerts valve gear mounted externally for easy servicing, resolved the conflict between extreme power and tight clearances. Union Pacific commissioned the design strictly as a calculated mechanical response to a mountain that refused to move. During the heavy hauling years of World War II, Union Pacific No. 4014 entered daily service, translating complex engineering into raw industrial power. Assigned to the Cheyenne, Wyoming locomotive pool, the giant engine became a constant presence on the overland route. It was an era when national survival depended on the absolute reliability of domestic supply lines, and the big boys answered that demand by moving approximately 1 billion ton-miles of essential war freight. With 16 driving wheels biting the steel rails, No. 4014 hauled heavy freight trains carrying coal, steel, military equipment, and raw materials over the Continental Divide. The sight of the massive locomotive, trailing a mile-long line of cars and sending a towering plume of exhaust into the western sky, defined the golden age of American rail power. The locomotive was a physical manifestation of industrial confidence, standing as proof of what American builders could achieve when pushed to the limit. The performance of the 4884 fleet proved that railroad operators could conquer any geographical obstacle. No. 4014 ran almost continuously, its heavy machinery subjected to punishing daily schedules across the rugged Western Territory. Engineers and firemen pushed the machine to its limits, relying on its horsepower to keep the transcontinental supply lines moving. The engine functioned as a self-contained power plant, converting water and coal into immense tractive effort. At this point in history, No. 4014 represented the absolute maturity of steam technology. It belonged to an era when heavy machinery was the undisputed driver of economic growth. This was a world built on coal, water, and steel, where the sheer physical size of a locomotive stood as the ultimate measure of progress. The locomotive performed with exceptional reliability, proving its worth over the punishing mountain passes day after day, cementing its place at the very pinnacle of American industrial achievements. In the late 1940s, a different kind of power began appearing on American main lines. It arrived quietly, carrying neither the dramatic visual theater of steam nor its massive operational footprint. These were diesel-electric locomotives. Initially relegated to switching yards and light passenger duties, these machines quickly began expanding their reach into heavy freight territory. For decades, steam had been the undisputed foundation of rail transportation. The massive infrastructure of water towers, coaling docks, and specialized maintenance shops across the Union Pacific system existed solely to support coal-burning giants like No. 4014. But the arrival of the diesel-electric locomotive challenged this entire industrial framework. The transition was rapid, representing a systemic realignment of railroad economics rather than a sentimental farewell. Union Pacific, despite its heavy investment in the world's largest steam engines, could not ignore the shifting reality. The railroad's operating environment required absolute efficiency, and the cold logic of the balance sheet began to favor the new technology. Steam was no longer the default path forward for modern railroading. Even as No. 4014 continued to conquer the Wasatch grade, the ground beneath its 68-inch driving wheels was shifting. The technological transition was total. Railroad executives began to view their massive steam fleets as complex, high-maintenance relics of a passing era. The very foundation of the steam age had cracked. A new standard of motive power had claimed the high iron, and the era of the great steam giants was drawing to a close. The victory of the diesel-electric locomotive over steam was a matter of basic thermodynamics and operational economics. A steam locomotive is an inefficient thermodynamic machine, converting only about 6 to 8% of the coal's energy into actual movement at the drawbar. Diesel-electric engines achieved thermal efficiency rates of over 25%. For every dollar spent on fuel, a diesel engine delivered 3 to 4 times more pulling power to the rails. Besides fuel efficiency, the daily physical demands of steam operations became an intolerable financial burden. A machine like No. 4014 required constant, intensive human intervention. Before a steam locomotive could turn a wheel, a hostler spent hours gradually firing the boiler to build pressure without damaging the steel sheets. After every run, crews had to dump ashes, wash out the boiler to prevent mineral scaling, and manually lubricate hundreds of exposed moving parts. Diesels eliminated this cycle of labor. A diesel locomotive could be started with the push of a button and kept running for days with minimal attention. They did not require water stops every 100 miles, nor did they require the massive network of water treatment plants, coaling towers, and ash pits that lined the Union Pacific route. By replacing coal fires with liquid fuel, railroads swept away an entire system of high-maintenance support facilities. Labor costs also fell. Operating multiple steam locomotives to move a heavy train required separate crews for every single engine, each demanding an engineer and a highly skilled fireman. Diesels utilized multiple unit control, allowing a single crew in the lead cab to operate 3 or 4 linked diesel units simultaneously. The savings in wages alone made the transition inevitable. As Union Pacific systematically retired its water towers and coaling docks, the operating ecosystem that sustained number 4014 evaporated. A steam locomotive cannot run in isolation. It requires a specialized industrial infrastructure to keep it alive. Once that infrastructure was dismantled, the big boys were no longer competing against a more efficient machine. They had lost the physical environment required to operate. By the late 1950s, the financial calculations of the diesel transition had reached the Cheyenne locomotive pool. One by one, the practical design of the new locomotives sidelined the steam fleet. For number 4014, this end did not come because of a mechanical breakdown or a loss of pulling power. The machine remained as capable of hauling thousands of tons over the Wasatch grade as it had been during the high-demand years of the war. Its retirement was the structural result of a changing network that no longer had a place for coal and water. On December 7, 1961, number 4014 completed its final run in revenue service. Union Pacific workers extinguished the fire in its massive firebox for the last time, closing a chapter that had defined American railroading. The locomotive was officially withdrawn from active service, its working life concluded. Behind it lay a record of endurance. Over 20 years of daily operation through the rugged terrain of Wyoming and Utah, the engine had accumulated 1,031,205 miles. Every mile had been earned under punishing conditions, showing the durability of its construction. Yet, as the last steam cleared from the Cheyenne yards, the support network built to sustain number 4014 was disappearing. The coaling towers stood empty, the water tanks were dry, and the skilled workers who understood the complex machinery were retiring. The giant was silent, sidelined by a railroad that had moved decisively into a different future. Instead of entering a scrap line to be cut apart by torches, number 4014 escaped the immediate fate of most steam locomotives. In 1962, Union Pacific donated the giant to the Southern California chapter of the Railway and Locomotive Historical Society. Workers prepared the silent engine for its final journey, dragging its dead weight west to the Los Angeles County Fairgrounds in Pomona, California. There, it became the centerpiece of the Rail Giant's Train Museum, resting on a short, isolated segment of track, surrounded by other relics of the steam era. For the next 52 years, the locomotive remained completely stationary, exposed to the warm California sun. Children climbed its cab stairs, and museum visitors touched its cold drive wheels, but the fire inside had vanished. The dry Southern California air protected its steel shell from catastrophic rust, keeping the massive engine visually intact. Yet this static preservation was fundamentally different from keeping a locomotive alive. Preservation in this environment meant arrest. The museum staff could paint the metal, grease the rods, and clear away debris, but they could not maintain the complex internal systems required for active operation. Beneath the cosmetic layers of black paint, the boiler remained cold. The hundreds of stay bolts, the heavy articulation joints, and the intricate valve gears became stiff and silent. The engine had survived the scrapper's torch, but it was now a monument, an oversized statue of a bygone era. It was preserved to be looked at, not to be run. In Pomona, number 4014 was safe from destruction, but it was entirely divorced from its physical purpose. It was a mountain climber confined to a flat, static patch of grass, separated from the main line and the specialized tools that once kept it breathing. For over half a century, it stood as a quiet reminder of what used to be, a sleeping giant, frozen in time. The popular narrative surrounding the silence of number 4014 often suggests the giant was simply forgotten in the California sun. The reality was far more calculating. Railroad executives and preservationists knew exactly where the locomotive was, but they also understood a harsh physical truth. Reviving the world's largest steam locomotive was a logistical and financial impossibility. Cold feasibility assessments sidelined number 4014. For more than half a century, any proposal to return the engine to the main line was immediately halted by the staggering scope of the work. Early calculations for a full reconstruction of an articulated engine of this scale started at millions of dollars, a sum that no private museum or historical society could ever hope to raise. The sheer physical size of the big boy meant that standard preservation techniques were useless. A locomotive weighing over 1 million pounds turned every routine maintenance task into a heavy industrial challenge. Standard railroad machine shops no longer possessed the massive lathe beds required to turn 68-inch driving wheels or machine the massive crank pins. The specialized tooling needed to fabricate custom leaf springs, heavy boiler sheets, and massive articulation joints had been scraped decades earlier. Any repair required custom manufacturing, converting a restoration into a multi-million-dollar engineering campaign. Even the boiler, a massive pressure vessel, was a liability. Decades of static display left the internal stay bolts and steel sheets vulnerable to undetected corrosion. A single structural failure under 300 pounds of pressure would be catastrophic. Beyond the engine itself lay the complete erasure of its supporting environment. Steam locomotives are open system machines that require constant external sustenance. By the late 20th century, the network of water-purifying plants, coaling towers, and ash pits had been systematically demolished. A restored big boy had nowhere to drink and nowhere to fuel. Running number 4014 on a modern railroad meant inventing mobile, self-contained support systems that did not exist on the modern grid. The loss of human capital presented another barrier. The generation of boilermakers, pipe fitters, and firemen who understood the temperamental behavior of a high-pressure articulated boiler had retired. The intricate skills required to hand-adjust Walschaerts valve gears or monitor the complex expansion joints of a pivoting frame were no longer taught. Operating a big boy required a level of specialized expertise that had vanished from the American labor pool. For decades, the decision-makers at Union Pacific and within the preservation community had to balance sentiment against the hard reality of engineering. The verdict remained unchanged year after year. Number 4014 was too heavy, too expensive, and too complex. The giant remained stationary because the modern world had stripped away the entire industrial ecosystem required to make it breathe. In the summer of 2013, the decades-long consensus of impossibility shattered. Union Pacific made an unexpected public announcement. The railroad was reacquiring number 4014 from the Rail Giants Train Museum in Pomona. They rejected the idea of another cosmetic paint job or a simple relocation to a different static park. Instead, Union Pacific committed to a full, operating restoration, aiming to return the world's largest steam locomotive to active mainline service. The decision reversed 52 years of organizational and engineering assumptions. The project was championed internally by Ed Dickens, the head of Union Pacific's heritage operations, who viewed the giant as an active, living monument rather than an obsolete relic. With the 150th anniversary of the Transcontinental Railroad's golden spike approaching in 2019, corporate leadership saw a clear opportunity to celebrate their historic legacy on a national scale. Unlike private museums or historical societies, Union Pacific possessed the heavy industrial facilities, engineering staff, and corporate capital required to finance a multi-million-dollar locomotive overhaul. By taking back ownership, the railroad transformed the project from a volunteer-led hope into a fully funded corporate mandate. For the first time since December 1961, the discussion around number 4014 moved from preservation by arrest to the physical reality of steam and steel in motion. The locomotive was no longer destined to sit silently under the California sun. The giant was going home to the Cheyenne steam shop, where the immense task of rebuilding the world's largest steam locomotive would finally begin. The Cheyenne steam shop is a red brick fortress of heavy machinery, one of the few places left on Earth capable of hosting an undertaking of this scale. In 2014, the work began not with assembly, but with total demolition. To rebuild Union Pacific number 4014, the Heritage Fleet crew under Ed Dickens had to strip the locomotive down to its bare steel bones. This was not a routine overhaul, it was a forensic teardown. Every pipe, valve, appliance, and sheet of insulation was removed, exposing a raw boiler shell and two massive, empty frames. The sheer scale of the engine meant that standard tools were useless. The shop floor became a forest of heavy cranes, specialized hydraulic jacks, and custom-built scaffolding surrounding a metal carcass that weighed hundreds of tons. The heart of the restoration centered on the boiler, a massive pressure vessel that had spent more than half a century corroding from the inside out. Federal Railroad Administration regulations mandated a complete, ultra-precise inspection of every square inch of the boiler plate. Boilermakers and engineers crawled inside the cramped, dark interior of the shell. They found hundreds of stay bolts, the essential steel rods that hold the inner and outer boiler sheets together under immense pressure, damaged by decades of moisture and coal soot. The team had to cut out and replace over 500 of these stay bolts by hand, a grueling process of drilling, heating, and riveting that mirrored the original manufacturing methods of 1941. Every weld, thread, and seam had to meet strict modern safety codes, requiring rigorous non-destructive testing and ultimate certification before the vessel could ever hold steam again. Simultaneously, the mechanical crew tackled the locomotive's running gear. The driving wheels, measuring 68 inches in diameter, were dropped from the frame and inspected. The massive crank pins and axle journals, worn unevenly from decades of service and static display, required machining to restore perfect concentricity. Because standard railroad shops no longer possessed lathes of this size, Union Pacific had to contract specialized facilities, sending the crank pins to the Strasburg Railroad in Pennsylvania for precision machining. Meanwhile, key suspension parts like the heavy leaf springs were entirely worn out. Because no domestic manufacturer could replicate these massive, multi-layered spring assemblies, the team had to source custom fabrications from specialized firms in Germany and the United Kingdom. One of the most complex engineering challenges of the entire rebuild was the fuel conversion. To make number 4014 practical to run on a modern railroad network that had long since abandoned coal, the steam team had to convert the firebox to burn heavy oil. The coal grates and the mechanical stoker were removed. In their place, engineers designed and fabricated a custom draft system and installed an oil burner designed to atomize number 5 fuel oil within the massive firebox. This conversion changed the physical behavior of the combustion chamber, requiring precise mathematical calculations to ensure the oil burner could generate the 6 megawatts of thermal energy required to boil thousands of gallons of water. Year after year, the craftsmen of Cheyenne labored over the inert metal, slowly transforming the cold, static monument back into a functional, high-pressure machine. In the early morning hours of April 9, 2019, the cold silence inside the Cheyenne steam shop ended. Mechanics fed fuel oil into the rebuilt burner and threw a lit torch into the firebox. A low rumble grew into a steady roar as the oil ignited, heating the thousands of gallons of water surrounding the freshly riveted boiler plates. Slowly, over several hours, the pressure gauge climbed toward its operating limit of 300 pounds per square inch. For the first time in 58 years, Union Pacific number 4014 was alive, breathing steam under its own power. This first fire-up was not a ceremonial exhibition. It was the direct operational proof of a 5-year rebuilding campaign. Every joint, valve, and custom-machined staybolt had to withstand the extreme forces of high-pressure steam. Weeks of final testing culminated in May 2019, aligning with the 150th anniversary of the Golden Spike, the completion of the Transcontinental Railroad. On May 2nd, number 4014 backed out of the Cheyenne yard under its own power, ready for its inaugural mainline run. It was accompanied by Union Pacific living legend number 844, but the spotlight belonged entirely to the big boy. As the heavy throttle opened, steam rushed into the 4 massive cylinders. The 68-inch driving wheels bit the steel rails, sending a rhythmic, deafening blast of exhaust into the Wyoming sky. The articulation joints pivoted smoothly as the locomotive cleared the yard limits and accelerated onto the main line. This was the moment the restoration was proven, not on a static display stand or in a museum catalog, but in the heat, noise, and raw motion of an operating machine. Number 4014 headed southwest toward Ogden, Utah, retracing the very rails it had conquered during the high-demand years of the mid-20th century. Thousands of spectators lined the tracks, drawn by a sight and sound that had not existed on an American mainline since the twilight of the steam era. The physical effort of the Cheyenne steam crew had translated back into dynamic industrial power. The world's largest steam locomotive was no longer a dormant artifact. It was once again a functioning reality of the high iron. Today, Big Boy 4014 does more than haul freight. It pulls the past directly into the present. In an automated age, this titan reminds us of our limitless potential. Some legends are simply too powerful to remain silent. What vanished marvel should we bring back next? Let us know in the comments.